In this problem, a firefighter slides down a fire pole, and firefighters, they control their descent speed, creating friction between his hands, his feet, and the pole. So this friction is a non-conservative force that will dissipate energy. Energy then will not be conserved in this problem. It's important to say that energy is not destroyed. Energy is just transferred as heat created by friction into objects that are outside our system of interest, which in this case is the firefighter. So the heat will go into the atmosphere and into the pole and dissipate and will be lost by the system, but it exists in the universe. So we know that the mass of the firefighter is 110 kilograms. He starts from rest, so his initial velocity is 0, and he descends a vertical distance of 6.3 meters. So if we measure the position of the firefighter from his feet as a reference, the initial height of the feet is 6.3, and he will eventually hit the ground that will be at a vertical position of 0. So that's the final position of the firefighter. So the height that he descends is h 6.3 meters. We know as well that the speed when he hits the ground, or an instant before he hits the ground, is 3.1 meters second. And the question is, what is the average frictional force between the pole and the firefighter? And again, we know this frictional force is what controls the speed of the firefighter. So we need to find the frictional force, which in this case will be kinetic friction. And it's always important to keep in mind what is the question. We need to know always what is the quantity we are trying to calculate. So we will use conservation of energy to solve this problem. And in this case, the relevant types of energy that will be present is kinetic energy, final time. Then we have gravitational potential energy. And the final total energy is equal to the initial total energy. So we have an equivalent sum of energies for the initial time on the right of the equation, and we need to consider the energy that has been dissipated as heat. In this case, friction is what produces that energy, and the energy lost by friction or any non-conservative force present in the problem is just the work done by the non-conservative force. So to summarize, we have on the left the total final energy. On the right, we have the total initial energy. And in addition, we have the amount of energy dissipated by non-conservative forces. Since the initial velocity is 0, we know that the kinetic energy at the initial time will be 0. The final position, the final height, is 0. So the final gravitational potential energy will be 0 in relation to the level of the ground. So our equation then simplifies, and we will have on the left the final kinetic energy, on the right the initial gravitational potential energy, and again the work dissipated by non-conservative forces. So let's write these quantities in terms of other variables. We know that the kinetic energy is 1/2 mass velocity square. The gravitational potential energy is the mass times g times the height, in this case h, which is 6.3, and the work done by non-conservative forces, in this case is the work done by friction. The friction force is acting upwards, and the velocity of the firefighter is downwards. So since the friction is opposite to the displacement, the work done by friction is negative, and by definition the work is the force times the distance traveled, which in this case is the height. From this equation we can isolate what we need: the force of kinetic friction, and we can simplify a little bit this expression. And we are ready to plug in the numbers. The mass is 110. Final velocity. The height is 6.3. And after plugging in these numbers, we get, and rounding, we should keep 2 sig figs because all the data in the problem is given in 2 sig figs, so we get 990 newtons. So one thing that is necessary to highlight here is that we don't have to write the force of kinetic friction in terms of the normal force and the coefficient of kinetic friction, because in this problem we should get the force of friction from the parameters that are related to the energy of the object. And we're done with this problem.